Thank you very much for the introduction. I want to start by thanking the organizers for putting together such a thought-provoking and inspiring workshop, and also for the invitation to give a talk here today. So as the title says, I will be telling you about quantum reference frames in this talk. Quantum reference frames can be understood as a research field that lies at the intersection of several disciplines. On the one hand, we have quantum information and quantum foundations, quantum field theory, gauge theories, and also ultimately quantum gravity. And as such, we work on many different problems, some of which I'm putting here for reference. So more on the quantum information and quantum foundation side, we're interested in understanding which properties of, let's say, quantum states or observables are not absolute but depend on the reference frame. We use quantum reference frames as concrete tools for predictions, in particular in scenarios where space-time is not classical. In quantum gravity, we have the problem of time, where quantum reference frames can be used to sort of encode time evolution into correlations with a clock. And more in gauge theories, we can construct just observables, material reference frames, and edge modes. And then in quantum field theory, we also have type reduction. So the plan for today's talk is that I will start with a few brief motivations for why several people or different people care about quantum reference frames. I will then give you a brief introduction into one of the approaches to quantum reference frames, and we'll then look at two separate case studies for why or showing why quantum reference frames are useful tools. On the one hand, we'll look at them as a tool for non-classical spacetimes. I will then briefly tell you about resources in quantum reference frames and to what extent they get, there's a trade-off between them, changing perspective, and how this relates to subsystem relativity. And we'll then look at a second case study and try to understand how quantum reference frames play an important role in regularizing divergences in quantum field theory. And then I will end with a brief outlook and some research directions that I'm currently working on. Okay, so why care about quantum reference frames in the first place? Well, in a world with fundamental symmetries, almost all physical quantities must be understood as relative to some frame of reference. Without reference points, there is little we can meaningfully say about the world around us. And this is why, either explicitly or implicitly, we always rely on reference systems, whether it's a clock to mark time or a ruler to measure distances. And these reference frames are not just abstract concepts, they are actual physical systems. And if we take quantum theory to be universal, applicable to all physical systems, then they should ultimately also apply to the reference systems that we use to define or describe systems and observables. And as such, reference systems are treated as not as fixed external entities, but as actual physical quantum systems that can be in a superposition, they can be entangled with other physical systems, and they evolve according to the principles of quantum theory. Now, in more gauge theories and maybe quantum gravity, reference frames have long been understood as important. For instance, they allow us to construct gauge invariant just observables, frame justings, relational observables. If we are given some bounded spacetime subregion, then quantum reference frames allow, in the form of edge modes, to encode information about physical boundary conditions. And in quantum gravity, as I said earlier, the problem of time evokes the need for some timekeeping reference frame in order to describe evolution. And then maybe as a third motivation for why people here might care about quantum reference frames is their role that they play in the regularization of gravitational entropies. Now, observable algebras of local regions in quantum field theory are typically of type 3, and as such, don't admit a finite trace, and there's no well-defined entropies. Now, recent work by many people, including Chandrasekaran, Longo, Pennington, and Whitson, have shown that adding a quantum observer to a quantum field theory leads to the reduction of the type of the Neumann algebra of observables. And this quantum observer can be understood as a quantum reference frame. I will try to give further arguments for this later on in the talk. And this has led to the slogan that CLPW is page footers. Page footers as sort of the underlying mechanism on which we have built quantum reference frames. So adding a quantum reference frame to a quantum field theory in low energy quantum gravity regularizes gravitational entropies. All right, so now to properly introduce quantum reference frames, I'm going to be following an approach called the perspective neutral approach. I just want to mention here that there exist other approaches to quantum reference frames, and I'm very happy to answer all sorts of questions about them either after the talk or in the breaks later on. I want to consider here very general systems that transform under some symmetry group G. This presence of the symmetry group leads to a redundancy in the description. I can have two different descriptions of the same physical situation that can be understood as just different descriptions in different coordinate systems. Typically, we remove this redundancy by imposing some constraint and by gauge fixing. So I'm working in some kinematical phase space or kinematical Hilbert space. I impose some constraints. I have the gauge orbits on this constrained surface, and then I gauge fix. And this is what we do in quantum reference frames. In fact, a quantum reference frame choice can be understood as a choice of an internal subsystem. So nothing we add on top, it's an internal subsystem that we already have in our description. And it's used to break this symmetry and to act as a reference for the remaining subsystems. And as such, we have a dynamical reference system that allows us to parameterize or gauge fix the orbits of the symmetry group in this Hilbert space or even the observable algebra. And what we are interested in particular is to describe the gauge invariant dressed or relational observables of our theory. Okay, so the way we go about this in full generality is that we consider some reference system R and some general system S. And we assume from the start that they both carry a unitary tensor product representation of some unimodular, locally compact symmetry group G. So we take that each group element G acts as such with a tensor product on R and S. And then what we do is we look for the globally invariant states. So those states in the kinematical Hilbert space which remain invariant upon the action of the symmetry group on the states. And the result of this we call the physical states living in the physical Hilbert space. And they can be obtained either as imposing some constraint. Very often this is going to be some Hamiltonian constraint that we impose, or equivalently as the result of applying some coherent group averaging projector. So this is just an integral over the entire symmetry group where we let the representation act on our frame and the system. And the result of this is going to be some gauge invariant, in fact, highly entangled physical state. So this can be understood as some coherent group averaging that encodes sort of all perspectives at once. All right, so in order to make or to write down a state of our reference system, we first need to build a so-called coherent state system. These are generalized coherent states a la Gilmore-Perelomov. So these consist of a choice of a representation that our frame carries and some set of states that we construct. We assume that the group acts transitively on this coherent state system. And assuming this, we can choose some normalized seed state E, where E is the unit element of the symmetry group, and then we generate all other states, orientation states of our frame, just by letting the representation act with the respective group element on it. Importantly, we need to construct this coherent state system in a way that it gives rise to a resolution of the identity. This is important such that we get a sort of correct probabilistic interpretation of the states of our reference frame and what it means to measure them. In fact, if we have such a resolution of the identity, I can then define so-called covariant POVMs, positive operator valued measures, with effect operators as such. And then I can make sense of measuring my reference frame, applying some effect operator, obtaining some outcome, and making sense of what is happening on my system of interest as a consequence. Now, there are several different types of reference frames that we consider in the literature. Here, I'm going to limit myself to so-called complete frames. Complete frames are those on which the symmetry group acts regularly. So we have a free and a transitive action. There exist more general frames, but in this talk, I will only talk about those two. And for complete frames, we have on the one hand so-called ideal quantum reference frames. These are particular systems which carry not just any, but the regular representation of the symmetry group. And as such, they have associated Hilbert space L2 of G. And any two frame orientation states, G and G dash, if G and G dash are not the same group element, they're going to be orthogonal. And as such, they are perfectly distinguishable, almost classical-like frame orientation states. A physical example of this would be some clock transforming under time translations with an unbounded energy spectrum. So I would have L2 of R as my Hilbert space. A non-ideal complete quantum reference frame is just a reference frame that carries any unitary representation of the symmetry group. As such, I can have that different frame orientations are assigned non-orthogonal overlapping coherent states. And an example of this would be a clock transforming under time translations with an energy spectrum bounded from below. All right, so after having constructed these reference frame states, I can now write my physical states simply as an integral over the symmetry group of a respective orientation state on my frame and the associated state on my system. And then if I measure or condition on a particular orientation of my frame, I obtain the conditional state on my system. So this is the state of the system conditioned on the frame being in orientation G. The whole time you can just be thinking of a clock and conditioning on the clock showing a particular time. In fact, this whole construction can be seen as a generalization of the so-called Page-Wouters formalism. The Page-Wouters formalism was constructed in the 80s as an attempt to solve the problem of time. It's a so-called timeless formulation of quantum theory, where instead of having some time parameter in our theory, we have a timeless state that consists of a clock state that is highly entangled with the system of interest. So we sort of have all of the time evolution encoded in the correlation between the system and the clock. And I can just look at the clock at a particular time. And what I will see on the system is just the time evolved state of the system. And so this quantum reference frame construction can be seen as a full generalization of this idea for general symmetry groups. And as I said before, what we care about here are the relational or dressed observables. I obtain those by taking some kinematical observable of my system that I'm interested in. I attach the reference frame in a particular orientation to it, and then I average over the symmetry group. So I take the conjugation of the two. So this can be understood as a gauge invariant encoding of the kinematical observable on my system conditioned on my frame showing some particular orientation. All right, so this concludes sort of the brief introduction for one reference frame and a system. Now, in quantum reference frames, we're very interested in what happens when we change perspectives between different quantum observers. So here, I just do the same thing, but now I consider two reference frames. I have a reference frame R1 and a reference frame R2 and some system of interest. I take the tensor product of their respective Hilbert spaces to construct my kinematical structure. Again, I impose some constraint, maybe a Hamiltonian constraint, the coherent group averaging, and I obtain this physical Hilbert space structure. We call, in our literature, we call this the perspective neutral structure because it's set to encode all of the perspectives of all possible quantum observers at once in the correlations of these globally invariant states. And once I have constructed this structure right here, I have the choice of reducing into whatever perspective I want. For instance, I could choose the perspective of my first reference frame R1, condition on that frame being in orientation state G1, and I obtain in the reduced Hilbert space of S and R2 the conditional state of that. Just as much, I could just reduce into R2 being in orientation G2, get the reduced Hilbert space right here, and nicely, all of these Hilbert space here are isometric. So I can just unitarily change between the perspectives of these different quantum observers. Okay, so this concludes the brief introduction to quantum reference frames, at least in the perspective neutral approach. And now I want to get to sort of the first case study of how quantum reference frames can be used to solve actual physical problems. So here we want to look at non-classical spacetimes, and in particular, look at a very simple scenario. In fact, I want to look at the scenario in which I'm a very powerful experimentalist, and I can place some gravitational source mass into a superposition of two different locations. And what I'm interested in describing is the motion of some test particle in the vicinity of this gravitational source in superposition. And in fact, when we looked at this problem some time ago, we wanted to do so while remaining agnostic about the nature of the gravitational field sourced by this mass in superposition. So not assuming whether it should be quantized, in what sense it is quantum, maybe it's classical. Of course, I could just choose some top-down approach in which I have quantum theory and GR sort of emerging as the limits of some larger theory of quantum gravity. But instead, what we choose to do is to take a bottom-up approach, a first principles approach to this problem. In fact, we want to take the principles of quantum theory on the one hand and of some known theory of classical spacetime, GR, QFT uncurved spacetime, and try to combine these principles and see how far we can push them. In fact, the concrete recipe that I want to use for this problem at hand is the following. The first ingredient are just the symmetries of some known physical theory, in this case of classical spacetime, and I add to it the superposition principle of quantum theory. What I get as a result are so-called extended symmetry principles. Extended symmetry principles simply posit that the laws of physics are invariant not just under any classical symmetry transformation, any classical reference frame change, but under quantum reference frame changes. And I do want to point out here that that is an assumption that we haven't tested. We know that all classical reference frames are equal, but we don't have concrete evidence that necessarily all quantum reference frames are equal. Okay, so what this recipe allows us to do is to make concrete predictions in the regimes in which these assumptions are applicable without the need to rely on perturbative methods. So the strategy that we're going to use here is that we're going to start in the original reference frame, maybe the reference frame of the laboratory in which I prepared this superposition. And I then will change quantum reference frame from the probe particle into the frame in which it's the gravitational source that's in a definite position. Now, because quantum reference frame changes leave invariant the relational degrees of freedom between systems, in this case, the coordinate distance between the probe and the respective location of the mass, as a consequence, I have that my probe particle is in a superposition of locations. But importantly, the gravitational source is in a definite state. So now here, in this frame, I can use a classical theory of gravity. And I can solve the problem in this new reference frame. So let me change into it here. I can here use whatever physical theory I want. I can do Newtonian gravity. I can do full-on GR if I want to. Now, in this paper right here, we computed just the geodesic motion and the concrete quantum phase acquired by this probe particle on the respective geodesics. And then I can just transform back. And assuming that this transformation is one that leaves the laws of physics, the equations of motion invariant, I can now infer what happens in the original frame. And there I will have that the probe particle will just fall in a superposition of geodesics, acquire different quantum phases on its way and become entangled with the respective locations of the mass. And this entanglement, for instance, is something that I could in principle measure and verify. So this is sort of the summary of this argument. Rather than going from 1 to 4 immediately, making assumptions about the gravitational field sourced by this mass in superposition, I can circumvent this, use classical and tested physics right here, and then move back. And the assumption that I put in is that this step, 1 to 2 and 3 to 4, leaves the physics invariant. If the probe particle is some quantum clock that is ticking at a certain rate, then what we get as a result, or as a prediction here, is that this clock will tick in a superposition of different time dilations, getting entangled with the respective location of the mass. Okay, importantly, what this argument yields are predictions that are perfectly consistent with just assuming that this mass in superposition sources a superposition of gravitational fields. So it's consistent with me just writing down a superposition of the sort of classical gravitational fields. However, my claim here is that this argument is also valid beyond perturbative approaches in which I could use, for instance, linearized quantum gravity. A sort of immediate and maybe a bit extreme example is that of a black hole. If I place some probe in the vicinity of a black hole that I prepare in a superposition of different locations, then at this location of the probe, there won't be a common background around which I could treat the black hole as a perturbation. Okay, so what to do? Well, if I apply the strategy of changing into the frame of the black hole, it is only the probe particle that's in a superposition, but I'm dealing with a classical standard Schwarzschild background. And I can then apply the same argument of circumventing this really difficult question right here by just using classical GR on this side. And the predictions we get are equivalent to considering just 2 different backgrounds right here in a linear superposition. Okay, now before proceeding, I do want to draw your attention to a quite interesting effect that we have when changing between different quantum reference frames. So you see here on the left-hand side that it's the massive gravitational source that's in superposition. And here on the right-hand side, it's just a probe particle that's in superposition. And what we claim, assuming this invariance under quantum reference frame changes, is that these are 2 descriptions of the same physical situation. So which system is in superposition and which one is in a definite state is just a frame-dependent relative statement. In an even simpler scenario, I can consider 3 spin 1/2 particles, A, B, and C. So these are just 3 systems that can be found in either one of 2 states or linear superpositions of them. I can write down the state right here. So this is the perspective of A on B and C, and you see that this is a product state. Now, when I change reference frames into the frame of particle C, which is in a superposition relative to A, I apply a quantum-controlled symmetry transformation. So this is sort of this line at the bottom of the triangle, changing from one perspective into the other. For the case of Z2, this is just an operator right here. And the result of this quantum reference frame change is the state right here. In the perspective of C, I have that A and B are maximally entangled. Okay? So I'm mapping with my unitary quantum-controlled symmetry transformation, I'm mapping a product state into a maximally entangled state. Now, this is not surprising once you realize, so superposition and entanglement seem to depend on the frame. But this is not surprising once you realize that quantum reference frames are choices of tensor product structures. So I have here on the physical level, or maybe even on the level of the physical algebra of observables, all perspectives at once. But then once I choose one particular reference frame, one particular quantum observer, this corresponds to me choosing a particular observable algebra. In particular, I'm looking at the observables on B relative to A and the observables of C relative to A, and I generate the full algebra. So this corresponds on the Hilbert space level to a particular TPS relative to A. On the other hand, I can choose the same for C. So observer C is now imposing a certain subalgebra structure of my algebra of observables. On the level of the Hilbert space, this corresponds to a TPS relative to C. And so once we realize this relativity of subsystems is merely a consequence of us choosing different TPSs on our physical Hilbert space. And realizing that the sort of subsystem structure changes under changes of quantum observer, it's no longer as surprising to realize that entanglement depends on the choice of subsystem. Okay, so what do we do now with this coherence and entanglement being frame dependent? It had been clear for quite a while in the community that there is some trade-off between superposition and entanglement when you change between quantum reference frames. But it wasn't really clear where these resources were coming from. And these are really powerful resources in quantum information protocols. So it would be nice to understand how to generate this entanglement by a mere change of perspective. And what we found quite recently is an invariant quantity that combines entanglement and subsystem coherence measures, and that is conserved under all quantum reference frame changes. So in particular, if you take the sum of these two quantifiers, this holds on the one hand for entanglement entropy and relative entropy of coherence, and on the other hand for linear entropy and L2 norm of coherence, all quantum observers will agree on this sum of these two resources. Okay, and here when I say coherence, I mean so in a particular basis, because coherence is basis dependent, I mean the basis induced by the symmetry group. So if you have time translations, I'm talking about the basis of time orientation states. Okay, to make an analogy with electromagnetism, we know that in different Lorentz frames, I have different amounts of the electric and the magnetic fields, and two Lorentz observers would not necessarily agree. However, they would agree on a conserved quantity, which is the Lagrangian density of the electromagnetic field tensor. And so as such, we say that superposition or coherence and entanglement can be understood as two sides of the same coin, just described in different quantum reference frames. Okay, I just want you to keep in mind this result for the very end of the talk when I will talk about sort of the outlook and future research directions. Before doing so, I want to get to the second case study, which is on quantum reference frames for regularizing divergences in quantum field theory. Now, as I said at the beginning of this talk, and I'm sure many of you are aware of, observable algebras of local regions in quantum field theory are of type 3. And therefore, we don't have any finite trace. We can't compute well-defined states or entropies. Now, in 2023, CLPW showed that adding an observer quantum system with some clock as a type 1 algebra yields to type reduction to type 2. In this construction, they used results by Takasaki on cross products, and this type 2 allows us to compute gravitational entropies. Now, since then, there have been many works on this appearing in the literature and many generalizations of this result. This is by no means an exhaustive list of these results, but importantly, in our community, in the quantum reference frames community, this was extremely exciting because it was immediately clear that this observer, type 1 algebra, carrying a clock, is nothing more and nothing less than a quantum reference frame. In fact, there were two separate teams of people working on quantum reference frames that showed in 2024 that this observer in this cross-product construction is a quantum reference frame. In particular, the procedure that's followed by CLPW is very closely related to this Page-Wooges construction. So as a reminder, the the quantum reference frame construction can be seen as a generalization of Page-Wouters for more symmetry groups, but in the case of time translations, it's really just that. And so this led to the slogan of CLPW equals PW. So let's review the result of this paper in just a bit more detail. What we're dealing with is, as a gauge group, we have the one-dimensional translations in time. So we have some representation carried by our clock, which just moves time forward. And this has a Hilbert space L2 of sigma c, where sigma c is the energy spectrum of the clock Hamiltonian HC. So this can be R for some ideal clock, and a non-ideal clock would be one with an energy spectrum bounded from below. We can construct, as I showed you before, the clock orientation states, and for a non-ideal clock, I will have that two different frame orientation states, two different time states will in general have some overlap. So these will be some coherent states. And from this, I can construct a POVM element, covariant POVMs, and I can write down some clock operator on my clock. Okay, so what the authors in this paper did is that they looked at some low energy gravitational system, some effective quantum field theory, coupled to multiple observers. So multiple clocks or observers carrying their clocks on their distinct world lines. They constructed the kinematical Hilbert space by just taking the tensor product of all the clock Hilbert spaces, as well as the QFT Hilbert space. And they imposed a single Hamiltonian constraint, which was just the sum of all the Hamiltonians, with the taking a modular Hamiltonian for the QFT of some fixed cyclic and separating QFT state. Okay, so as a first step, we can look at the subalgebra of gauge invariant operators and find that it's type 3, and in fact, it's nothing more but multiples of the identity. If I then look at the relational or dressed observables that I obtain by taking some observable of my QFT, dressing it to a particular state on my clock, so clock showing time tau, and then I group average over this in the way that I always do in order to get my dressed observables, I get this algebra of observables right here. This is not enough yet to construct this cross product of CLPW. I need, in addition, a second type of transformations, and these are so-called frame reorientations. So while normally we consider the action of the group like acting equally on the clock and the system in order to keep the relation between the frame and the system the same, frame reorientations are transformations that only act on the reference frame. So this can be understood as just a transformation that puts forward or backward the time shown by the clock. And if I combine these two types of transformations, the dressed observables on the one hand and the clock reorientations on the other, these authors showed that this gives me precisely the cross product construction. And as such, we have now an algebra of type 2. To be a bit more precise, adding an ideal quantum reference frame, so one with L2 of R, some ideal clock with unbounded energy spectrum, I get type 2 infinity. And if I add a non-ideal quantum reference frame, I get type reduction to type 2-1. So maybe a bit surprisingly or counterintuitively, adding a bad clock with finite resources seems to be better in order to compute gravitational entropies. All right, so as I said, the authors in this paper didn't just consider a single observer with a single clock, but they consider an arbitrary finite number of clocks and of observers traveling on their distinct world lines. And as such, they can compute or write down operators for arbitrary states, any subalgebra of subregion and subset of clocks. Importantly, what they find is that two distinct observers traveling on distinct world lines within the same subregion can see distinct entanglement entropy of the quantum field theory. So we have some observer dependence of gravitational entropy. So on the one hand, if I have, let's say I simplify to just two clocks, C and C dash, on the one hand, I'm describing the entanglement entropy of some state of the QFT with respect to some clock C, and this is just different from the entanglement entropy of the QFT dressed to some other clock C dash. And so in this sense, we recover this idea of the subsystem relativity, and here it gives rise to a relativity of entropy. Now, overall, if I look at the total entropy of all the degrees of freedom in the subregion, including all of the observers, all of the clocks, then this entropy is still observer independent. All right, and so now just for a few current questions and research directions that I'm interested in and that I would love to hear your opinion or input on. Let's look at three concrete open questions. The first one is concerned with this trade-off between resources that is quite apparent in quantum reference frames. But the question is, to what extent can we recover this in some gravitational setting? So here I showed to you how there is some combined quantity of entanglement entropy and some quantifier telling me how much coherence there is in the other reference frame. And on the other hand, in the gravitational setting, we find that we have frame-dependent entanglement entropy. So to what extent is it possible to take this result right here, extend it to the gravitational or QFT setting, and see if there is any sort of conserved quantity that all quantum observers, all clocks, would agree on? For the second question, to what extent can at least some UV divergences in quantum gravity be understood as the price of refusing to specify an observer? Do type 3 algebras arise when we insist on frame-independent descriptions? I remind you here that actual measurements, operational measurements, always involve choosing some reference system. And given that all physical observers have ultimately finite resources, is this a hint that we should maybe always be working with some type 2 instead? Which infinities in quantum gravity more generally can be understood as artifacts of trying to do physics without specifying an observer? And then as a last question, looking at the black hole information paradox or black hole evaporation more generally, we see that different quantum reference frames see different subsystem structures and thus entanglement structures. When we describe black hole evaporation, in particular in the page curve, we presuppose some fixed frame-independent subsystem structure, in particular radiation subsystem. So is there any way to understand this as if the subsystem structure depends on the reference frame choice, are there any particular choices of quantum reference frames which just have fundamentally different operational access to the correlations between early and late radiation? And could this make the transition between entropy increase and decrease fundamentally observer dependent? And with these three questions, I thank you for your attention, and I look forward to any comments you might have.
You have plenty of time, Edward.
Just a minor comment on your first case study. The formulation with a superposition of the Earth in two different positions is vague, because in the spirit of your story, it requires clarification what that means.
Yes.
That's such a statement, as you essentially said at the beginning, has to be made relative to a reference frame. For example, physically, one would perhaps mean relative to the distant stars or to other bodies in the solar system. If that was what the question meant at the beginning on the left-hand side, then your two pictures are actually not equivalents, because the setup where the Earth or the atom is in a superposition of different positions relative to the rest of the solar system, those setups are not equivalents. In fact, they're highly inequivalent, because for example, atom is really a photon of long wavelength. In one case, we might see interference phenomenon, in the other case, we'd be hard-pressed to see them.
Yeah, thank you for that comment. Indeed, in the paper, we took into account that, of course, if there are any more systems than just the two systems, in particular some laboratory, the fixed stars, any system in general, then even though that you might be able to trace that out on the left-hand side, if you change reference frames towards the right-hand side, the proparticle will be highly entangled with any other degree of freedom in the description. So in particular, highly entangled with the distant stars, the laboratory, and so on. So what we looked at was particular bounds on sort of what can the interaction be, the gravitational interaction, and how far away do other systems need to be for me to be at least approximately able to trace out those degrees of freedom. So I agree that on sort of this like equivalence between these two physical descriptions is only correct if we are in some otherwise empty universe and we only have two physical systems that we consider. And in fact, this leads to, I didn't have time to talk about this here, but this leads to some extremely interesting situations. One of this is called the third particle paradox. So the third particle paradox is like whether or not I include my third particle into the description, I might have decoherence or no decoherence because of entanglement with some possibly extremely far away fixed star. I do want to mention that we looked more generically at sort of superpositions of semi-classical space-time scenarios where we took all of these arguments into account. But yeah, thank you for the comment.
Go ahead. Could these transformations that change the quantum reference frame, would they do something weird to an off-diagonal state? Like when you had the state with the probe was in the superposition of two things and the Earth was in one, you change it to the probe is in one and the Earth is in two. What if you had a situation where both were in a superposition, like maybe you had the probe in two things, like you had a state where the probe is in two positions, tensor product, the Earth is in two positions. Could this state in any way be acted on by something to make it simpler or something?
Yeah, very good question. So, maybe more generally, the question is, given some superposed and entangled state, can I find some quantum reference frame in which it becomes a product state? Like, to what extent can I transform away superposition and entanglement using these extended symmetry transformations? And in fact, what I can never transform away are the gauge invariant degrees of freedom being in a superposition. So in this case of the relative distance, if you give me some, let's say, entangled state where the distance between the two systems is different in different branches of the superposition, I will not be able to simultaneously localize both systems. However, if you hand me some super complicated entangled state where it just so happens to be that in every branch the distance between the two is the same, I can apply some quantum control translation that maps to a frame in which they will both be localized. So really it becomes about what are the gauge invariant and the gauge variant degrees of freedom. Entanglement and superposition of gauge invariant degrees of freedom will not be transformed away by any extended symmetry transformation, and anything else should in principle be able to be transformed away.
I wanted to ask about, you made the statement that these reference frames are somehow internal to your system. And so anything that you're doing, you are addressing your observables to, you want that to be dynamical in this framework, you want that to be described by a quantum system. And so in the spin example, it makes sense that there are 3 spins in the system and you choose one of them to be your reference and you're described. So in that sense, that is part of the system. But when you write L2 of G for this arbitrary symmetry group, that seems to be something external you're putting in, right? Like, in what sense is that internal?
Right. I would say, given all of my systems, like analogously to the spin example, I could just be handed n number of systems. I assumed from the start that all of them carry a representation and in fact a tensor product representation. So I'm assuming from the start that I have systems S1 to Sn where I have a representation U1 of G tensor Un of G. And now I can choose any one of these tensor factors or any set of tensor factors as my reference frame. Sort of I choose from the systems that you hand me, I can choose any subsystem relative to which I'm going to address all of the others.
Start with Maxwell theory in, say, Minkowski space. There the degrees of freedom are fixed, right? Like in that, you still, for your L2 of G, you have to add something more to Maxwell theory.
Yes, right? Yes. So if you want an L2 of G reference system and you don't find an L2 of G factor in what I'm giving you, you can't do what I just told you. But even for Maxwell theory, let's say you have some U1 gauge theory on a lattice and you write down the action on the lattice, maybe I can identify one tensor factor that I'm going to say, I'm going to address things to this one. So it doesn't have to be L2 of G, right? It can be some highly non-ideal frame as long as I find some tensor factor in what you hand me that carries a representation, and I can construct these coherent state systems. And there's some caveats, but it's quite general.
Between CLPW and PW, you need that L2 of G structure, right?
Yes, I agree. So if you just start with the QFT and there's no observer, there's not going to be, you're not going to have a chance. I agree with this. But I would argue that maybe starting with the QFT only is not a good model.
Okay. I'm not sure if I understood the statement correctly, so let me check. You seem to be saying that there's a non-trivial empirical question that could be settled by experiment of whether, classical invariance under changes of reference system extends to the quantum level. And I'm trying to, if that is the statement, could you say more about how we would settle that empirical question experimentally?
Right, that's the next question that we've been thinking about for a long time, and it seems to be a really hard question. In the simplest way, what I would need to do in the experiment to test whether 2 quantum reference frames are equally valid in their descriptions of physics would be to somehow measure in one reference frame, that could be classical just from the laboratory perspective, and then I would need to be able to take that detector and sort of place it in some possibly superposed state and see if it still registers the same probabilities, the same sort of detector clicks. However, this is, yeah.
To Edward's question, I think you pointed out correctly that you need there to be nothing else in the world. So you would need to put yourself into a superposition of, you know, two different places or whatever, right? Which is not, I mean, I don't see what the process would be for comparing the different versions of yourself, because there's still only one of you. You're just in a superposition and actually drawing any kind of conclusion at the end.
Right. I agree that if we want to do this, like really show that they're fully equal, this is going to be very hard. But also this argument that we are making here is only on the level of quantum states. I think if we restrict ourselves to the relevant observables, which should, in the case of a superposed detector, should be observables that allow me to sort of trace out the rest of the world. So I should be looking at observables that care about the system, like the two systems at hand, for instance, and that act in a way that I can forget about the interaction with other degrees of freedom. I think this is going to get us closer to this. So, or put differently, I need to be able to shield the interaction with other degrees of freedom that would get highly entangled with the reference frame.
I think it's at least not clear to me whether it's in principle a well-defined question, what it would mean to compare the outcomes of different versions of yourself. Of the experiment that you performed in a superposition.
Okay, but I think we're conflating a few things here. I'm not placing myself necessarily in the superposition. I do think that this question can be settled just without giving too much weight to me being an observer and the detector being a measurement outcome. I think there should be a way of constructing this in the laboratory. Maybe with certain loopholes, certain assumptions where I can test at least partially this principle without having to be in a superposition myself or entangled with other systems.
Go ahead. You define the quantity called the coherence of C. How is that defined?
It's so, for instance, can be the relative entropy of coherence. So the basis I'm working with is this basis of the ket G states. So it's the basis induced by the symmetry group. And this particular coherence quantifier is the difference between the von Neumann entropy of only the diagonal elements of the density operator, this minus the von Neumann entropy of the full density operator. So it quantifies how many off-diagonal elements there are in this basis in terms of the von Neumann entropy.
So you assumed at various stages that the group was locally compact, at least. If the observer is more complicated than that, does the story or these arguments change significantly?
The well-defined was mathematically changes in the sense that it's going to be really hard to write down this coherent group average. Personally, I don't see a conceptual reason for why a lot of the lessons we draw from here should suddenly stop working once we go beyond that. So I'm personally quite optimistic about that holding beyond this, but just purely mathematically it's going to be hard.
So in your example, you consider the reference frame as some physical system, like for example, in a qubit system, you have an A or C.
Yeah.
What if I choose a reference system as some kind of logical degree freedom in the
That's in what degree freedom?
some logical qubit?
Ah.
So what happens if you consider?
Well, first of all, I think these could just be logical, like logical qubits if you want to. Are you asking about the reference frame being some larger system that consists of many subsystems?
Some logical degree freedom in a very complicated system.
I don't see a reason why the lessons we do here wouldn't stop working. I think that applies to this situation as well.
Yeah.
I don't think we've thought much about this question, but yeah.
The formula you wrote down about the sum of entanglement entropy and coherence, is that just the entanglement entropy in the sort of larger extended Hilbert space before you imposed gauge invariance?
No, we understand it as the entanglement entropy of the reduced state in the reduced Hilbert spaces.
But is it not?
There should definitely be a relation to what this corresponds to. That shouldn't be too complicated, but I don't think it's going to be quite the same because on the level of the physical Hilbert space, the system is going to be highly entangled with other things. And some of this entanglement goes away when you reduce into the perspective.
Okay, if there's no further questions, let's take a skip.